This is the video for the 5-0-Chem final exam practice quizzes, and I'm going to cover moles, percent composition, empirical, and molecular formulas. So the first question here says, if you wanted to convert from grams to moles, how would the conversion factor be set up? So if you're starting off with grams, with whatever number of grams you have, remember when you set up the conversion factor, whatever unit you start off with goes on the bottom, and whatever you're converting to goes up top. In a conversion factor, it's always grams per 1 mole, and the grams you would get from the periodic table, and that's what the molar mass is. Alright, so you would have 1 mole up top, periodic table, or the grams from the periodic table, which is the molar mass on the bottom, which then is this one right here, 1 mole over molar mass. Next question, if you have 6.57 times 10 to the 25th atoms of sodium, how many moles would that be? So always start off with the number that you're given and the units. 6.57 times 10 to the 25th atoms of sodium. And since you start off with atoms are going to go on the bottom. And we're going to moles, so 1 mole goes up top. Now when you're talking about atoms here in the conversion factor, atoms are really small, so you need that really big number, which is Avogadro's number to go with them, 6.02 times 10 to the 23rd. When you do this math, what you should get, if you do it right, is 109 moles. And since you start off with 3 significant digits, your answer should have 3 significant digits. That's why I round that off to 109. 15 moles of iron, they want to convert it to atoms. So start off with 15 moles of iron. Now since you're starting off with moles, that's what goes on the bottom, and you're looking for atoms, so that goes up top, and that's Avogadro's number again, and it's always 1 mole in the conversion factor. So now you're doing 15 times 6.02 times 10 to the 23rd, and if you do your math right, and actually check that on the calculator, make sure you're doing the times 10 part right, it's 9.03 times 10 to the 24th atoms. For number 4, the molar mass of potassium permanganate. Potassium on the periodic table is K, and it has a positive 1 oxidation number. Permanganate is a polyatomic ion, that's MnO4 with a -1. So when you put that together, you get KMnO4. So if we want to figure out the molar mass, what you have to do is list each element and how many you have of each element in that formula. So there's 1 potassium, 1 manganese, 4 oxygen. You multiply it by the molar mass off the periodic table, and you write all of that out. So you get 39.1 for potassium, you get 54.9 for manganese, and then when you multiply that out for oxygen, you get 64, and you add all of that up, and what you should get is 158.0 grams per mole. So what that's saying is if you have 1 mole of potassium permanganate, you would have 158 grams of it. Now remember this part, getting the oxidation numbers. You count left to right across the periodic table. The first column has +1. The alkaline earth metals, which is the second column, is +2. Then by the time you get to where aluminum is, that's +3. Then it's plus or -4, -3, -2, -1. And then the noble gases, since they tend to be inactive, they don't have an oxidation number, so we just say they're usually 0. Okay, number 5. What percentage of chromium is found in aluminum dichromate? So for this problem, whenever you see percentage, you think percentage is a part divided by the whole. Now aluminum has a +3 oxidation number. Dichromate is a polyatomic ion. It's Cr2O7 with a -2. So when you put all that together, you get Al, I'm going off the side there, you get Al2 Cr2O7 in parentheses with a 3 outside. So to get the percent composition, what we have to do is figure out the molar mass. So you set this up just like it's a molar mass problem, and you write down how many of each element you have. Remember, this 3 gets distributed by everything inside the parentheses, so now you have 6 chromium and 21 oxygen. Aluminum off the periodic table is 27.0, so when you multiply that out, that's 54.0. Chromium is 52.0, and when you multiply that out, that's 312. And oxygen is 16.0, and you multiply that by 21, that's 336. You add all that up, and it's 702.0 grams per mole. Now remember, I said percentages are a part divided by the whole. These are the three parts, and this molar mass is the whole. Now all we're worried about is chromium, so all I really have to do is take that 312 and divide it by that 702.0, and it's going to give you a decimal. It's going to be 0.444 repeating. You multiply that by 100, and you get 44.4%. So what that's telling you is chromium makes up 44.4% of this compound. Vanadium oxide is used as an industrial catalyst. The percent composition of the oxide is 56.0% vanadium and 44.0% oxygen. Determine the empirical formula. All right, for empirical formula, first thing you have to do is convert grams to moles. And since both of these percentages add up to 100%, it's nice and easy. You could just take that 56.0% and make it grams. We can do the same thing for the oxygen, 44.0 grams of oxygen. Now we have to convert this to moles. So we do a standard mole conversion at this point. Vanadium off the periodic table is 50.9 grams. So when you do that math, you get 1.10 moles of vanadium. Oxygen is 16.0 grams off the periodic table, and when you do that math, you get 2.75 moles of oxygen. Now you don't write this formula as 1.10 of vanadium and 2.75 of oxygen. You never have these decimals here like that. What we have to do is get the lowest whole number decimal ratio, and the easiest way to do that is divide both of these by the smallest number of moles. And the reason why we do that is that you automatically get one that is going to be 1 mole. And in this case, it's the vanadium because that was 1.10 moles, and that's what we divided by. Now the oxygen, when you do that division, you get 2.50 moles of oxygen. Now again, you don't write this with that 2.5 in there. But what we were doing is, if anytime it ended in 0.5 or something like that, you would multiply everything by 2. So the 1 mole of vanadium would become 2, and the 2.5 moles of oxygen will become 5. And now this is the lowest whole number mole ratio, 2 vanadium to 5 oxygen. Now the next problem is asking molecular formula. And that ends up being very similar to empirical formula, it's just a little bit longer. We start off the same way. The new part is this. It's giving you the molecular mass of really the molecular formula. But what we have to do is figure out the empirical formula first, because what we're going to work up to is the molar mass of the molecular formula divided by the molar mass of the empirical formula. And this is that 60.0 grams, that molar mass of the molecular formula. But we have to figure out the molar mass of the empirical formula. So that's why we have to do an empirical formula like we did for the previous problem. These percentages add up to 100% again. So we can just convert these into moles. Carbon has a molar mass of 12.0, and that gives you 3.33 moles of carbon. Hydrogen's nice and easy because that has a molar mass of 1.0 grams. So 6.7 grams will be 6.7 moles. And oxygen is 53.5%, but we change it to grams. And that's 16.0 grams off the periodic table. So when we do that math, it's 3.34 moles of oxygen. Alright, so now we're going to divide by the smallest of these moles because we want to get them to small whole number ratios. So that looks to be 3.33, which automatically makes these 1. And that's 1 mole of carbon this is going to be 1 mole of oxygen. So now the hydrogen, when we divide by 3.33, that's going to end up being 2 moles of hydrogen. Now this one works out well because they're all whole numbers. So our empirical formula ends up being 1 carbon to 2 hydrogens to 1 oxygen. Figuring out the molar mass of this is easy. Carbon is 12, hydrogen's 1 apiece, but there's 2 of them, so that's 2. Oxygen 16. When you add all that up, you get 30 grams per mole, and that is the molar mass of the empirical formula. So now what we have to do is this molar mass of the molecular formula divided by the molar mass of the empirical formula. This number was given in the problem. That's that 60 grams right there. So we get is that 60 grams per mole divided by the 30 grams per mole, and that gives us a ratio of 2. So what that's telling us is that our molecular formula is double the empirical formula. So CH2O now becomes C2H4O2, which should be one of the options here, right here, C2H4O2. So that's molecular formula. It's a long problem, but you start off doing empirical formula first.